So, so what we're going to do is let's review the exam. I don't understand why it takes this to download. What is happening? Like, this should not take, so it's like frozen. Like the movie. Okay, so the first thing that we wanted to do is we wanted to show a couple things were logically equivalent. I put problem 1 on here. I chose it very much for a reason. A fascinating thing on, I believe it was homework 1 or 2. We had an English sentence, and I said write the negations of it. A few of you misinterpreted that problem anyhow. But the last one, you were supposed to negate an and. And almost everybody, in fact, I don't think anybody got it correct. So the negation of an and is actually an or. That's the purpose of problem 1A on the exam. Does that make sense? So actually, let me pull it up for good measure. What is beeping? All kinds of things are beeping. Beep, 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 beep. It's on my mind, so I'm going to pull it up. I believe it's homework 1. Let me see. Let me double check. Yeah, on homework 1, problem 1E, we gave you a statement that the summer in Pittsburgh is hot and sunny. And you were supposed to negate that. And so the correct answer should be the summer in Pittsburgh is not hot or not sunny. It sounds funny to say that, but that's the correct way of doing it logically. And what most of you wrote is the summer in Pittsburgh is not hot and sunny, which is logically incorrect. So the point of the problem on the midterm is just that. So let me say that. So this is number 1A, and what I'd like you to do is we're going to prove that not P and Q is logically equivalent to not P or not Q. And what I would encourage you to do is compare with number 1E on homework 1. Like again, we're supposed to get something from this course. And messing up problems on the homework is cool. That's part of the learning process. And even messing things up on exams is cool. That's part of the learning process. Now, the idea is that we improve throughout the semester. So that ideas we messed up in August and September, we stop messing those things up in October and November. And eventually, we go from having this level of understanding and we've progressed. I mean, that's the way I'm always grading you guys at the end. Those of you who've had me in class before, I hope you realize that. Almost none of you, I guess, you know, your numerical grade is probably not very much what you, well, maybe you expected to get something, I don't know. But the point is I'm not just giving you a grade based on how many points you earned in the semester. Now, that doesn't mean that I don't use that. Obviously, that matters. The more points you earn, the higher your grade's going to be. But I'm not just going to say, well, you only earned this many points, and since that's a B out of the total, I can't give you anything higher than a B. Right? That's not how it works. That's not how at least I do it. So it's about seeing progress. It's about me being able to tangibly see that you've learned things throughout the semester. So that's sort of how I go about it. But anyhow, let's see how we would do this. And here is one correct way of doing this sort of problem. So let's use, I don't know, we'll use green. So here's the solution. Now, there's a few ways you can write this up. I've told you before how I like to do it. I like to put all the contestants, the guys playing, I want to put them down. And what I like to do is I like to do it from left to right. So as I'm reading from left to right, I want to list everybody who's participating in this particular claim. So the first two guys are the propositions P and Q. And then I'm also interested in P and Q. Then I'm interested in not P and Q. So that's the left-hand side of the table, or not the table, but the sort of the sentence that I'm trying to verify. Now, it'll be quite useful if we can separate these things with columns to make it look pretty. And so I'm going to just concentrate, since we're babies right now, I'm going to concentrate on only the left-hand side of this equivalency. I'm not going to look at the right-hand side yet. I'm only going to look at the left-hand side. And so what I'd like to do now is I need to follow the pattern. What's the pattern say? The pattern says, okay, I have two propositions, P and Q. So what are all the scenarios? Well, at this point, you should know if there's two propositions that there's four scenarios. Scenario one is where they're both true. The next scenario is where one is true and the other is false, and then vice versa. And then the scenario where they're both false. Clean this up a little bit. Now, what I would expect on a test like this is that most of you get this problem correct, because you're not under a timed exam. You're not sitting in a room without resources. I mean, this problem, you could easily look up the tables if you don't have them memorized. Now, I would encourage you to have them memorized, but I'm not going to be mad at you if you don't. Okay, so what's P and Q? Well, and is true in only one circumstance. The only time and is true is when they're both true. So this scenario is they're both true, bingo. Actually, I'm not going to use that color. I'm going to stick green. Okay, in every other scenario, they're false. Doesn't matter. The only time the and statement is true is if both of them are true. If both P and Q are true, P and Q is true. Otherwise, it's false. And of course, I wrote that down wrong. That was actually not on purpose. What kind of brain freeze I had there. And then we just negate this, so then it's false, true, true, true.
Wouldn't it be not P and Q?
Say that again?
I said, wouldn't it be not P and Q? Not just P and Q?
What do you mean? I'm confused by what you're asking.
Because you have not P and Q is equivalent to not P or not Q.
Yeah, I didn't do the right-hand side yet. So
Okay.
So all I'm doing right now is this is a table just for the left-hand side of the equivalence.
Okay, gotcha.
Now I have to do the other side. And there's options here. You can make this all in one table, and that's what I'm going to do right now. But you could also have two tables and show that they're the same. So what I'm going to do now is I'm going to put the guys who are the right-hand side in, and I'm going to use different color. So who's on the right-hand side? Well, I have a not P. I have a not Q. And then, of course, I have not P. This looks like a 7. Let's get that out of here. And then the last thing I have is not P or not Q. So I'm going to continue with using my pink here. And I'm going to separate these. So the negation of P is just, okay, well, what's P starting with? Well, P is true, so this would be false. I'm going to change my colors here. So this should be false, false, true, and true. And then this would be false, true, false, true. So how am I getting these values? I'm getting these values because I'm reading the second column and I'm taking its negation. Does anybody have a question about this? Okay, now I have to do the or statement. Now an or is interesting. It's the opposite in a way of the and statement. An or is true provided at least one of them is true, because that makes sense, right? Then I'm not lying to you. The good way to think about this stuff is ask yourself, when is a promise not being fulfilled? And so for an or statement, the only way a promise is not fulfilled is if one of the things, or excuse me, both things I'm promising happen to be false. So what we do is we say, okay, this means since both are false, or is false. And then the rest are true. And the key observation to make, which makes this what we say a sort of a verification by a truth table, is that this column and this column have the same truth values. And that is exactly what it means to say you're logically equivalent. Does anybody have a question about this? Now, this is not, I'm not just saying that this is the only correct way to do this problem. It's not, but this is a correct way of doing it. And the instructions did say use a truth table to verify. And one of the skills that we want you to be able to do in this course is construct truth tables. That's just a learning, what do they call that in education? It's a learning objective, right? Come on, teachers, is that what we call this? It's a learning objective. Have I told you guys lately that I love you platonically? It's been a while, right? There's all the negativity in the world, but I'm here to be happy. Make you smile. You had a crappy week. You had all these tests. I didn't help because I gave you hard tests as well, probably. Although some of you always think it's easy, but it's really not. Anyhow, so you got to know how to do this. A truth table is one of the most basic, and I don't mean this to insult you if you got it wrong, but it is I don't mean it in words of difficulty basic, but it's a fundamental thing. In a course of this level, you have to be able to construct truth tables, all right? So if you can't do it properly right now, get to work. Like my kid, she keeps saying, I want to do push-ups. I said, well, you better get some muscles because you can't do them yet. And she just sort of like does these weird things on the floor. It's very strange. Kids, you know what they say? I mean, kids really, if you want, it's so amazing how people, I tell you this all the time, people learn, and learning is such a cool thing. You never realize how learning works until you see children. And then you realize how learning works. Like you guys think if you just like think hard when you're laying in bed at night, you'll just learn math. You guys fail to forget you actually have to do math to learn it. You can't just pray on it or think real strong and say, maybe if I think real good tonight, it'll make sense. That ain't how it works. Just like Lydia can lay on the floor all she wants, unless she starts pushing like this over and over again and starts eating some damn protein, she ain't gonna be able to do any push-ups. All right, enough. I'm on a roll today. Ooh, I got a mask up. Like those jerks in my sheets who look at me because I have my mask on and they're too cool for masks. Too cool. It's a hoax. Damn libs ruining everything. All right. You know, speaking of logic, and I don't want to get political, but if your flag says "Make America Great Again," doesn't that mean that the last 4 years ain't been great? That's illogical. That's a fallacy, right? That doesn't make any damn sense.
That's why he changed it to keep it.
But there's a bunch of these jabronis who still fly "Make America Great Again" signs. I did like this one I drove past today. It said, F your feelings, Trump 2020. It's like, what world am I in? This is it. Welcome.
There's this couple out there from Andy's last night for dinner. This couple came in and they were older.
Oh,
And they were dressed head to toe in MAGA.
I love the MAGA
like
people.
Pants, masks, hats.
It happened. It really happened over the last 20 years where like like this political thing where if you're liberal in any way, maybe not like the loony liberals they show on TV, but even if you're remotely center, then you hate police, you hate soldiers, you hate America, right? This is what they've made. It's so weird. I saw the president's dorky son was tweeting about like only Trump people have American flags in their front yard. I was like, that's not true. Where do you get this? This is poor logic. Anyhow, let's get out of here. I'm having fun today. High on caffeine, guys. I think that's what it is. All right. But every time I see that stupid flag, I'm like, you would fail math 2050. That's poor logic. All right. The next one we want to do is also important because it's has to do with what we call the contrapositive. And that is, we want to show that P implies Q is logically equivalent to not Q implies P. Now, we've used this strategy to prove things. I wrote that wrong. This should be, let me fix this. This should not be that. Well, I guess you could say that, but logically equivalent, we've been using this symbol. So, I believe we've actually proved this in class, or it was on homework, and we've used this fact many times, and we will continue to, so it's worth us proving it, practicing it especially. So who are the players? P and Q are the players on the left-hand side, and then P implies Q. Those are players on the left-hand side. Let's get a color here. How about we use this dark green? That'll get our spirits up. Dark greens in the house. All right, and then once again, we have 4 scenarios: true, 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 false, false, true, false, false. What I should have done is I should have done all this with 0s and 1s in honor of you guys all wanting to be computer science people. Then you really would have had a brain aneurysm. All right, so P implies Q. P implies true. When we want to do the implication, P implies Q, there's only one time it's false. It's only false when we say a truth implies a lie. It's the only time it's false. So the only time it's false is if T then a lie, true then false. So that means that this is true. Whoa, that ain't good. Get my blue back. That means this would be true, this would be false, and then true, true. So that's the left-hand side of our sort of thing we're studying. Now let's get the right-hand side. We'll use this orange again. I was feeling that orange. Now who are the players over here? The players over here are not Q, not P, and then, oh, this is different. And then not Q implies not P. This is sort of like a suspect table. It's all crooked. It may have had a little bit too much to drink. All right, so what is not Q? Not Q is going to be the opposite of what Q is. So this would be false, true, false, true. And then not P is false, false, true, true. And then, of course, how do we read this off? It's only a lie in this scenario. So this is the only time a promise is not given. The other times it's true. And so we celebrate since these two match. We'll get our little red star. I was drawing stars for Lydia this morning. She's like, that don't look like a star. I said, you got to color it in then. Ain't that cute? It's like the Macy's emblem. I'm on a roll today. What's happening? It's been a good class so far. I've indoctrinated you with my liberal agenda. You've drawn stars.
Whenever I was in basic training, they had the targets that you shot that would go down on the rifle range had the communist star on the helmet.
Really?
Pink faces. And the drill sergeant was walking up and down behind us,
What year was this?
97.
I was gonna say they probably can't do that anymore, can they?
Same, I was alive.
Well, all right. So what was I doing in '97? I was just a joke. I was at the prom, doing what we do, man. I mean, so what were you in the Army?
Yeah.
I often wonder.
They said a lot of stuff then. that I
Yeah, we
wonder if
probably
they
wouldn't
say-
be get away with now. Yeah. I mean, I just remember like being a kid in elementary school in the '80s was quite interesting. It's just like Russia bad, United States good, communism evil, United States perfect. Boris Yeltsin, terrible person. Was it Boris Yeltsin? Was that his name or no? Who was the Russian president at the time? I forget, but he was the emperor of the USSR, I guess. The Union of the Soviet Socialist. How about this? There was an old globe that I confiscated in here years ago when I first got here. It was an awesome globe because it had East and West Germany on it and had the USSR. Not awesome in the sense that that's the way the world should be, but just a cool, like a collector's item. I like history. I'm like a history person. And then I accidentally had it thrown away. What are you laughing at over there? Aren't you guys sad you're not here? They're laughing at me. What?
Carly,
What? What?
Carly texted me. Said a radio prom would have been a sight to see.
You know, believe it or not, there's a video going around of me at the prom. So I'll have to have my buddy Spot bring it in. It's in VHS though. I don't know how we play it. It's no DVD. Oh my God, now Siri's listening to me. Oh my God, plus the Russians are probably listening to me too because I'm recording this. We'll be on YouTube, China bad. America good. That's what they told you. I'm serious. It's funny. We didn't even comment. Is today Columbus Day? We didn't even comment on that awesomeness yet. Man, we got to say, I know, we'll ignore it. We'll just wait till Thanksgiving, then we'll get really involved. All right, does anybody have any questions? That's my favorite. Does anybody have any questions on problem 1? Going once, going twice, sold. All right, let's move on to problem 2. Problem 2, again, it's worth us going through this. I hope you guys, even though you can have these whiteboards, I hope you're taking notes and thinking about how we're doing this. So for problem 2, I gave you 2 sets. You have A, which is the first 4 even positive integers, 2, 4, 6, 8. And then B is the first 4 positive integers. So what I wanted you to do is determine these new sets. So what is A union B? A union B is everybody who's in at least one of them. So A union B would be 1, 2, 3, 4, 6, and 8. So what does it mean to be in A union B? It means you're in A or you're in B, with a possibility you're in both. We call that the inclusive or. Doesn't mean one or the other, it means one or the other and the possibility of both. So for example, the number 2 is in both A and B, so it's also in the union. Now, what is the intersection? This intersection means you have to be in both. So there's only 2 numbers that are in both. That's 2 and 4. That's it. That's the only 2 numbers that are in both. All right, then the next thing is A take away B. So this is the one that usually gives us confusion. It means everything that's in A but not in B. So what's in A that's not in B? 2 is in A, yes, but it's in B. 4 is in A, but it's also in B. So the only elements of A take away B, or A minus B, or the difference A, B, is 6 and 8. Does anybody have a question about these first 3? These are the 2 basic ones. or the 3 basic ones, I should say. I keep getting rid of my thing. All right, so then the next one that we asked you to do is the power set. So we denote the power set with this kind of script A. And so this is the set of all subsets. Now it turns out, and we'll be able to verify this is true later, but if you've done enough examples, you'll convince yourself that if the number of elements in a set A is n, then the power set has 2 to the n elements. So for example, we have 4 elements in A. That means we should have 2 to the 4, 16 elements in the power set. Now you don't need to know this fact. To do the problem. It's just helpful if you've recognized that, because then you know you've gotten them all. So for example, the first thing is we have to include the empty set. That's always a subset of every set. That's that weird thing that scares us. Then we talk about all the singletons. The subset of just 2, the subset of just 4, the subset of just 6, the subset of just 8. And then let's talk about the subsets that say have 2 elements in them. So the first one would be, say, 2, 4. Then 2, 6. So what I'm going to do is I'm going to keep writing these up here. I don't want to switch pages. So this is kind of very bad, sort of O'Gradyist nonsense that instructors would get mad about. But it kind of looks sloppy. Or maybe we'll just go to the next page. Too bad I can't minimize one whiteboard and share 2 at the same time. It's very annoying. So the next guy would be, if I continue in this manner, the next guy would be, oh, I don't want that. Excuse me. How did I end it? Let's look. So we'll have our comma here. So the next guy on the next page, I already did 2, 6. So the next guy would be 2, 8. And then now I'm going to do all the subsets that have 3 elements. So let's do 2, 4, 6. And then how about 2, 4, 8? And then how about, I forgot, I didn't do this one yet, 4, 6, 8. So at this point, you might be confused, am I getting them all? So what I would encourage you to do is ask yourself, okay, are these all the subsets that have 3 elements, 2, 4, 6, 2, 4, 8? Is there any other way of doing it? 4, 6, 8. I got 2, 6, 8. No, I didn't. So I say, oh, I forgot one. I forgot 2, 6, 8. Did I forget any other ones? Well, let's think about this. How many total elements are there? There's 4. So if I'm going to pair them 2 at a time, I should think about what the 2 goes. The 2 goes with 4, a 6, and an 8, so that you can think about how many options there are. That's one way to ask yourself if you got them all. Another way is to just count. So right now, how many subsets do I have? I have the empty set, 2, 4. So this is 4 here, 7. Then I have 8, 9, 10, 11, 12. It looks like I'm missing 4 more. Now, the one that's always easy to remember is the set itself. That's always in there. So we know for a fact that the very last set is just A itself. So that would just be 2, 4, 6, and 8. But what we don't know is what are the other 3 we're missing? Which 3 are we missing? Say that again? What do you mean 4 and 6? Yeah, so that's a good point. So what happened is I only did the 2 pairs. I did 2, 4, then I did 2, 6, and then I did 2, 8. But what I forgot was the pair of the 4s, right? So I already have 2, 4, but I didn't do 4, 6. And I didn't do 4, 8. And then the last one I didn't get as well would have been 6, 8. So I have all 16 now. They're not necessarily in any useful order, right? So I could have done a much better job of, writing this up than what I did so that it looks a little more systematic. But nonetheless, I listed them all. Does anybody have any questions about this guy? So let me remind you. So this is a fact. So if the order or the cardinality of a set is n, then the power set has 2 to the n elements. So here, the order of A was 4. And so the order of the power set, or the cardinality, would be 2 to the 4th, which is 16. So that's something to keep in mind. Does anybody have a comment about this one? All right, so let's go to the next page. The next thing we wanted to do is take the natural numbers. So this is what? The natural numbers and intersect them with A. So what is this? What is this? We can write out what these are. This is, what are the natural numbers? That's 1, 2, 3, 4, forever and ever and ever, intersected with A, which is 2, 4, 6, and 8. So it turns out in this particular problem, this is just 2, 4, 6, and 8. That's the only elements that are both in A and in the natural numbers. And then the last one's a bit of, I don't want to say a pain, but it's sort of yikes. But we've asked you to do this on the homework before. So this is the set of all ordered pairs where the first entry is in A and the second entry is in B. So this would be something like 2, 1, then 2, 2, 2, 3, 2, 4. And then what happens with, what are the next ones? 4, 1, 4, 2, 4, 3, and then 4, 4, and then we have 2 more rows. 6, 1, 6, 2, 6, 3, 6, 4, and then lastly 8, 1, 8, 2, 8, 3, and 8, 4. Those are all 16 of the elements in the direct product A, or A cross B. Does anybody have a question or a comment about this catastrophe? Now, again, you guys might think some of this is pointless, and it might even seem so confusing. Sometimes things that are so simple, but they actually seem the most confusing. But again, this is something that we you know, these kinds of things these are some fundamental things in discrete math. So we're asking that you understand them. All right, so that's the first 2 problems. All right, now the third one we want to prove, and this is where all the fun begins, is we asked you to prove that this number is irrational. Now, I'm not going to go through the detail. Well, I guess I could. But the proof is very much similar to the one where we proved the square root of 2 is irrational. And that works anytime the number you're trying to prove is an even number, because you can use the following strategy. So let's look at this. So what we want to do is we want to assume that this guy is rational and show this leads to a contradiction. That's the strategy here. So by assumption, the square root of 110 is going to equal P divided by Q. Well, let me not use P and Q because that'll confuse you with the previous problems. How about N divided by M, where N and M are integers and they have no common factors. That is to say, what if square root of 10 was equal to, say, 2/8? Well, we would just say instead of 2/8, it would be 1/4, right? So that's our assumption. Now, what can we conclude from this assumption? Well, we can do a little algebra. And we get that 110 is equal to n squared over m squared, which is the same thing as saying m squared times 100 is equal to n squared.
Excuse me, Professor, could we go back to that last slide really quickly?
Sure. Yep.
Thank you.
Yeah. Say that again.
Okay, I'm good. Thank you.
Anybody else? I need some water anyhow. This is good. Even if you don't think I'm going too fast, just pretend I'm going too fast. That way I can get some water. I'm very erratic. Sometimes I go real fast. Sometimes I go real slow. Then I tell stories. Okay, so rational means it can be written as the ratio of two integers. But if I do that, then I can write 110 times m squared is equal to n squared. So what does this tell us? This tells us that this tells us, because the left-hand side has a factor of 2, right? So this means that n squared is even. And then we know this means n is also even. So that was a problem we did before. If your square is even, then the number itself has to be even. We actually proved that by contrapositive. Okay, so that means by definition, that 110 m squared has to equal 2 times, say, k squared for some integer k. Now, here's where the previous proof that we've done has to be sort of modified. Because if you remember, when we proved the square root of 2 is irrational, we did a similar thing, and the conclusion was that we found that n was even and m was even, and then that contradicted the fact that they didn't have common factors. But we can't necessarily jump to that conclusion yet, can we? Because what we now have is 110 times m squared is equal to 4k squared. But that doesn't necessarily tell us, or does it, that m is also even. We have to get a little cuter. What do we do? Anybody have any idea?
Go in a different direction from there.
So what did you do?
Uh,
That doesn't mean you're wrong.
Yeah, so the 110b m squared equals a squared. How do I explain this? Basically implies that m, for this to be true at all, would have to be 1.
Well, right. So, okay. So what do you mean by 1? Not necessarily 1. You're on the right track.
Well, because if, given the assumption that n and m, like the n squared over m squared is lowest common factors, lowest common denominators. I mean, I'm trying to put the word. Then it's in the simplest form, right?
Right. Okay. So, okay. So I think you're on the right track.
So their only common factor between the two of them possibly could be 1.
Right. Okay. So okay. So that's one way to think about it, and you're on the right track. But maybe we should say it's slightly different. So first off, there's 2 things we need to point out in order for that to come full circle. The one subtlety we do, we and this was my fault. I should have said it. I didn't. First off, it's clear that m cannot be 0, right? So you can't divide by 0. So that doesn't make any sense. So let's just make sure we put that in there. That m cannot be 0, but they're both integers. Okay, once we fix that, now here's one way to think about it. So we have 110 m squared is equal to 4k squared. Now, so let's divide. We can't divide by 4 because 4 doesn't go in the 110, does it? No, but 2 does it not? So let's divide by 2. So if I divide both sides by 2, what I end up getting is I get 55. I don't remember what letters I used. M and then K. I get 55 m squared is equal to 2 k squared, right? Now, 55 is odd. Would you guys all agree with me? So this means that if 55 is odd, then what must m squared be? So we had an exercise that anytime you take an odd number times an even number, their product is always what? So like, what's 6 times 7? 42. What's 5 times 6? 30. It's always even, right? So what we can conclude here then is what has to be even. If the right-hand side is already even, the left-hand side has to be even too. So this tells us that m squared, and hence m, are even. But this contradicts our assumption. So we assumed that it was a rational number in simplest form. And if we made that assumption, we correctly deduced that n and m had to share a common factor, at least one of them, that number being 2. But we assumed that that wasn't the case, so we have what's called a contradiction. Now, your reasoning is not wrong, but you're taking advantage of something we didn't learn about yet. And you're taking advantage of divisibility. So I want to stay away from. There's another way to think about this problem. And one of the things that we'll learn soon enough is called the fundamental theorem of arithmetic. And you learn about this as a student in probably middle school when you talk about taking a number and writing it as the product of prime numbers. But we didn't discuss prime numbers yet, so I want to stick away from your reasoning for now. But your logic and the reasoning that, so the question was, not the question, the point was that there's another way you can think about this without using this show that both numbers are even. And that strategy is a little more sophisticated, and it requires the definitions of what we call divisibility. And it also requires that we understand this notion of prime numbers. So we'll actually use that, the proof that you're suggesting, probably in a couple weeks.
Yeah. And then, like, the end of it, I feel like I kind of walked off the end. But
Well, because you're making assumptions that turn out to be true, but they're not obvious why they're true. But yeah, you could definitely reason this other ways, but this is sort of the standard way of reasoning it. Because you're not wrong. I mean, another way of thinking, which you could reason, is you can reason that you can write the square root of 110 in two different ways using an idea where you're talking about the order of numbers.
right.
But I just want to stick away from that right now because we didn't really talk about that yet.
And then,
Yeah.
you know, 10 squared is what, 120.
Right, so you can, right, that's
10
another way of
squared,
doing it.
11 squared, it's got to be in between those two, but there's no integer there.
But we don't know that yet. I mean, we know that, but we don't know that. So part of the thing we'd like to do is when we're doing proofs is we only want to use what we quote unquote know right now. And since really the only definition we've talked about is this definition of even and odd, and then the definition of rational, that we would like our proof to only use those definitions. It's not wrong what you're saying. It's sort of like, you know, we don't know that yet. I mean, you could argue that that's a silly thing, but in math, we often play that game where we're only supposed to use what we've known. A good example of that is in calculus, we typically introduce the exponential function and some other, like logarithms early on, and some of you might remember that your textbook was Calculus Early Transcendentals, and then there's other books that don't say early transcendentals. And the whole thing is that from a development of mathematics, it's really difficult to define the exponential and logarithmic functions. And so what some calculus textbooks do is they wait until you have the necessary calculus to define them. But then other people say, well, we want to know what the derivative of these things is. So we introduce them early, even though we don't define them correctly, just so we have them for example purposes. And because you use them in chemistry or biology or something like that, finance. So it's this idea of when do we want to allow you to use some fact, right? Does that make any sense, Jared? But nonetheless, there are other ways to do this. This is just one of them. And heck, you might even argue, if you wanted to nitpick, you might say, O'Grady, how do I know that m squared is even just because you wrote it that way, right? Like you might say, is it true that the product, if a product is even, then one of the products has to be even? And the answer is yes. Right? So what I'm saying is, how do you conclude that m squared is even? Well, one way to think about it is you say, okay, I know that there has to be a factor of 2 on the left-hand side. Why do I know that? Because the right-hand side has it. And so if 55 doesn't have a factor of 2, who must have it? M squared. Does that make sense? You can think of it that way. Yeah.
But if let's say m is odd as well, won't that make it even as well?
That's good. As I said, yeah, right. You see, you have some subtleties, right? Right. So there's a slight flaw here. Very good. So, right. So what do we have here? Well, we have this. So a common error. Notice I didn't finish the proof yet, right? So a common error is to do this, and a few of you actually made this sort of assumption is this is not what I wrote here is not true. And you just told me that. I could take 2 odd numbers, right? can the product of two odd numbers give me an even number? Is it possible to take two odd numbers and get an even number? Let's think this is good. Is what I just crossed out in red true, or is it not true? Or can I make this deduction? This is an important point. The words we use in math, or we use this thing, is something necessary. Is it sufficient? And they mean two different things. I mean, look, you could, just for scratch work, you could say, okay, let me take, here's what we're saying. So here's the question. Does 55 times m squared being even imply that m is, well, first off, that m squared is even. Because if we get that m squared is even, then we know m is. But does that, look, we know that 55 times m squared is even. We know that. How do I know that? Because it's equal to 2 times something. That's the definition of even. It's equal to 2 times k squared. That's even. The question is, can we deduce then that m squared has to be even?
Did you say yeah? Because you said-
I mean, I said yeah, but Abdullah says no.
Yeah, no, I'm wrong.
I didn't say you're wrong yet. You got to be careful. It's not obvious reasoning. And look, this is what happens, though, because we start doing examples in our head to get an idea for if we think it's true or not. Now, I can prove that this is, in fact, true. I can prove that this means m squared is even. I mean, if you wanted to prove it, you could have said, let's assume it's not, and then you get a contradiction. But it is true, because if the right-hand side has a factor of 2, that factor of 2 has to be somewhere on the left-hand side as well, because they're equal, right? Again, and this is the deeper idea that I was alluding to with your point, is that every number has what we call prime decomposition. You guys did this, you did factoring trees. I guarantee you did in like 6th or 7th or 8th grade. You take a number, they probably teach you guys this in math teaching school for elementary students. You know, take a number and you make a little tree, you break it down into its prime factors. So what we have is the right-hand side is already factored 2 times k squared. The left-hand side is factored. I know we didn't talk about that yet, but you know what it means, 55 times m squared. And so since there's a factor of 2 on the right-hand side and the right and left are the same thing, then that number 2 has to be a factor on the left-hand side. Does that make sense? So this is, in fact, true. But it's good. It's worth questioning these things. That means you're learning. Right? And then it also means you're learning when you go home and read this and say, I have no idea what he's talking about. Any other questions about this problem? I think it's good that we nitpick at these things. You have a question? I don't mean that to be rude. I never know when you're talking if it's muffled or you guys are doing your own thing. Do you understand what I'm saying? Yeah. Oh, okay. I just want to make sure I'm not ignoring you guys. I don't want anybody writing at the end of the semester, oh, Grady doesn't answer my questions. I know you're going to complain I don't answer your emails, but what I need is the questions that I want to make sure I answer.
You're fine on email.
I know I've been getting much better. I've started making like email folders so that I don't miss stuff that matters. It's weird. I started setting times a day where I'm solely answering emails instead of just trying to keep up randomly here and there. I mean, email was such a great idea when it first hit the market. Now it's just like, especially when it's on your phone, and then it's a train wreck. All right, the next problem is one that causes issues because you guys are thinking about it from the wrong perspective. So number 4, here's the function we have. It takes 2 integers and it computes them in this manner. And we want to know, is it a bijection? And the answer is no. And what we need to do then is explain why. Well, there's lots of ways to do this, but the first thing I would encourage you to do, if you think something's a bijection, that means you have to prove it's both one-to-one and onto. So what's often, at least in my experience, one of the easier things to do is try to prove it's one-to-one. And you're going to find out that you can't do that. And the reason you can't even prove that it's one-to-one is because it fails real quickly if you look at what's happening from a symmetric standpoint. So a good rule of thumb is anytime you have a function that has two inputs and one output, think of symmetric stuff. And I don't necessarily mean symmetric like left and right or up and down. I mean, think what happens if you plug one pair in and then maybe do something to that pair, like negate it or flip them. And we saw this with even the simplest square function, like the square root, the squaring function, x squared. That fails one-to-one miserably because the negative and positive inputs give you the same output. So this thing is not a bijection because it is not even one-to-one. So let's see why. If I take, for example, 3 and -2, if I plug that in, what do I get? I get 6 minus 6 plus 5. And then if I take, for example, if I take -3 and +2, I get -6 plus 6 plus 5. And both of these equal 5. And that in and of itself is all the verification I need, because I just showed that two different inputs gave me the same output. That negates the definition of one-to-one. It doesn't meet the definition. So what is the definition? Let's think of this in terms of all that scary language we learned about earlier in the semester. The definition of one-to-one means the following. It means for all input that spits out the same output, those input have to be the same. So the negation of that is just find one. What's the negation of for all? The negation of for all is there exists one. And we found one situation where the definition is not satisfied, and hence it can't be one-to-one. Now, is it as easy as this for you to learn it as I'm saying it? Like, no, this is, you're thinking here. This is not obvious. But in fact, there's nothing special about 3 and -2. I just chose them because it was the first one that came to my mind. But there's other examples you can choose here that are going to produce the same output.
So on the midterm, like,
This is all you have to do. This is it. Now,
stop, but then I was like, wait.
no, I mean, look, that's okay because that's a learning experience for you. The thing is I wrote this problem. You could say it's unfair because if it's a bijection, there's a lot more to show. Yeah, no duh. But guess what? It ain't a bijection, so you don't have to do all that. Right? So a common thing is just because we ask you if it's a bijection, that doesn't mean that it necessarily is going to be. And so what's easier to do? Prove something is a bijection or to verify that it's not if it's not? And typically, no matter what, it's usually easier to verify that it's not when it's not, right? Because if you're trying to prove it's a bijection when it's not a bijection, then you're doing something that's doesn't make sense. But again, this is the first time you're asked to do this, so you can't get discouraged. You can't get up. Of course, you're going to make a mess of it. No one's expecting you to write up polished answers necessarily right away. So
Yeah, I fundamentally misunderstood that.
that's okay. Most people do. That's why it's funny. I put this, but here's what's going to happen. I'm probably going to put the same damn problem on your final. So don't fundamentally misunderstand it in a month.
I thought that the arguments for the function were Cartesian product.
No. Okay. No. What do you mean by that? I mean, and it is.
Well, so in that case, wouldn't these two things?
No, because look at the domain. The domain is all integers. So 3 comma negative 2 is definitely in Z cross Z, and negative 3 comma 2 is in there. You're thinking about it in the context of those sets of maybe like A and B where there's 4 elements. But we're not. I'm allowing the first and second input can be any integer. We're not limited to like 4 or 5 elements like if in that example up above. Do you understand what I'm saying? That's a good point you brought up, because your brain. So the question is, the question was, how is this legal to try both of these? Well, I think what's happening is you were getting confused because in the case where you have 2 finite sets like A and B, then the Cartesian product is going to be finite, and it might not have this sort of pair in there that we needed. But if you look at the domain of this function, it's Z cross Z, so that is legal. Do you understand what I mean?
Yeah, I'm at what I did.
Yeah, it's okay. I mean, it's a good, now you know. Well, hopefully now you know.
I definitely screwed that up.
That's okay. I don't expect many people not to screw things up. All right, let's knock these last 2 out. By the way, is the homework due tonight that I said? Okay, let me change that since we didn't get a chance to talk. We'll make it due Wednesday. How's that sound? Is that cool with you guys? Here, I'll do that. It'll just be like magic. I'll go right here, homework 5. We'll go to edit, and then we'll change the due date to Wednesday the 14th. There you go. Everybody's happy now, right? All right, let's finish these last 2 problems. I hope you guys will get some learning out of this. So the last one was a sequence that I asked you to define in a certain way. So this is number 5. So I've got a lot of emails about this, and maybe it's the way I worded it, but anyhow, we're starting with a sub 0. We're calling that 5, and then a sub 1 is the previous guy plus 3. A sub 2 is the previous guy plus 3. And so there's a very sort of simple formula for the recursion. And then this thing goes forever. So the first 10 terms are not terribly difficult to figure out. You start with 5, then it's 8, then you add 3 is 11, then add 3, 14, then 17, and then 20. And so what we're asking, though, is instead of defining it recursively, could we define this explicitly? So there's a couple ways to view this. I asked to find a formula for a sub n. And if it wasn't clear what I meant by part B, well, once you read part C, I hope it's then clear. Because it's going to take you a hell of a long time to figure out a sub 468 doing it this way. Right? So again, you might say, well, I'm confused by part B. And I say, okay, well, even if you're confused, use the context of the next part. What I mean by a formula, and maybe I could have been a little more specific, perhaps, is that there's got to be some quick way to compute this, because I'm not going to ask you to write this out 100 or 468 times. Right? All right, so here's a little trick that might help to get an idea for the pattern. So let's take a sub 3. We know a sub 3 is a sub 2 plus 3, right? And then, but what is a sub 2? A sub 1 by definition plus 3 plus 3. So another way of writing this is a sub 1 plus, I know it's 6, but I don't want to write it as 6. I'm going to write it as 2 times 3. And then I can plug in, what is a sub 1? A sub 1 is a sub 0 plus 3. And then this is plus 2 times 3. And so if I regroup this, this is a sub 0 plus, how many copies of 3 do I have now? Now I have 3 copies of 3. And then lastly, I'm going to plug a sub 0, and that's 5. So I get 5 plus 3 times 3. Does anybody have a question about this? So all I'm doing is I'm writing out, what I'm thinking into myself is, can I write a sub 3 so that it doesn't depend on anything except the very first guy or the number 3 itself? And so maybe it's not clear to you yet. So then maybe I say, okay, let's do this again. Let's play this game again with a higher number. So maybe I go, to like a sub 6. So a sub 6 will be a sub 5 plus 3. Well, what's a sub 5? A sub 5 is a sub 4 plus 3. And then that's plus 3. And so another way of writing this is a sub 4 plus 2 times 3 again, right? Because I have 2 copies of 3. Now, what's a sub 4? A sub 4 is a sub 3 plus 3 plus 2 times 3. So I can write this as a sub 3 plus 3 times 3. Now, I know what a sub 3 is. I got it from the previous page. It's 5 plus 3 times 3. So this becomes 5 plus 3 times 3. And then this is plus 3 times 3. So I can write this in a clean way as 5 plus. How many copies of 3 do I have? Well, you might think of that as 9 plus 9 or 18. I like to think it as 6 copies of 3. And the reason I'm thinking of it this way is I think I found a pattern. Aha. A sub k is 5 plus k times 3. And note, it checks out. If you replace k with 0, you get 5. If you replace k with 1, you get 8. If you replace k with 2, you get 11. So it checks out. It matches our pattern. That's the key observation. And so then you can easily go to a calculator and get a sub 468. You just take 468 times 3 and add 5 to it. Does anybody have a question about this? Comment? A few of you emailed me about it. I tried to give you a good hint. I hope it worked. I don't know. And when I was looking at these, grading them, there's some suspect reasoning, but that's part of the learning process. All right. So does anybody have a question about this? I'd like to talk about 6 and then move on. All right. So, oh, by the way, let's just, just to kill the dead horse, at the end of the day, a sub 468 just becomes 5 plus 468 times 3, which you'd have to plug that into a calculator. So if I did this correctly, I got 1409. Anyhow, let's get the last problem before we got a few minutes. But the last problem, here's what you have to do. You have A is the set of all numbers that are integers that look like this. And then B is the set of all numbers that look like this. So K is an integer. Your job is to show they're the same set. So the way you do that is you have to show A is a subset of B and B is a subset of A. So to do this one, I'll do this one, and then you guys can hopefully figure the next one out yourself. It's pretty much the same exact argument. So let N be in A. What does that mean then? That means that n is 4k plus 1 for some k in the integers. Now, I want to show that I can write this as 4k minus 3 for some k. It doesn't have to be the same k. So that's the big mistake here, that as amateurs you don't understand, that it doesn't have to be the same integer. It can be any integer. These sets are both defined as for some integer k. So here's the cute way of doing it. Note that 4 is the same thing as what? Well, let me write it this way. Let me say that 4 minus 3 is equal to 1, so that I can rewrite this. I can say n equals 4 times k plus 4 minus 3, which is the same thing as 4 times k plus 1 minus 3. And this meets the requirement. So and again, this is typically something that is confusing to us as beginners. I understand that. But what this means is I can write this as 4 times, say, j minus 3. And I'm done. I've written it as 4 times integer minus 3. And really, you just reverse this argument to go the other way. So right now, you might even be saying, well, this is a weird problem. Wow. Actually, recognizing when numbers can be written certain ways is very, very important in all kinds of applications. So we're going to spend some time talking about divisibility and its importance with this understanding numbers, particularly prime numbers. And there's all kinds of applications of that. Anyhow, guys, thank you very much. I appreciate it. Please bring questions. We'll talk about homework. If you want, you can send me emails, Michelle. I forget which ones you'd mentioned, but I'm happy to email you if you want to send me an email. All right, gang. Thank you very much. I will see you Wednesday. Cool. All right, guys. Take care.